So if you look at this particular title, we find the simple two terms here. The first one spectral and another one is the factorization. Having the background from the mathematics here, we can have the factorization, and that factorization is with respect to the representation into the frequency domain. This term spectral designates to the frequency domain representation here. So let us see how the random processes can have the spectral factorization here. So very first of all, we shall begin with how exactly we denote the power spectrum of a random process. Especially here we take the case of a wide sense stationary process. So here we consider the representation of a wide sense stationary process to be a random here, x of n, and the power spectrum, as previous case we have denoted p suffix x as a function of e to the power j omega here. So here representation, so this is nothing but the power spectrum, and this is our random process which is denoted by x of n, hence into the suffix we have denoted this particular x. So this power spectrum is a real valued, it is a positive, and also it is periodic function of omega. Omega is the angular frequency. Now here we can extend with this power spectrum representation for spectral factorization, provided the condition is that if this power spectrum, which is also called as power spectral density, is a continuous function of the angular frequency omega, then these particular characteristics imply that the power spectrum px of z into the z domain can be factored into the product of the form represented here. So in the first point we have represented the power spectrum by the use of Fourier tool here. So into the Fourier tool we have the representation of power spectrum px as a function of e to the power j omega. So this is also the one way to represent into the frequency domain. The another alternative, sometimes convenient, is to go with the z transformation. So here it is the representation px as a function of z. So now in this mathematical expression, this px of z, one and the same, that is the power spectrum, can be factored into the three terms here. Here it is the first term, that is sigma 0 squared here. The second term is capital Q as a function of z, and the third term here it is Q conjugate as a function of 1 upon z conjugate. So the representation of the power spectrum in such the three factors, those are confined to the frequency domain. Here the tool has been the z transformation here is nothing but the spectral factorization with respect to the power spectral density of a discrete time random process here. Now moving further, as we have already assumed that the wide sense stationary random process can be x of n here. So considering it, there are certain ensemble averages of the first order as well as the second order. We consider the second order statistical characterization in terms of the autocorrelation function that we usually denote small r suffix x as a function of k here. And just now we had the representation of the power spectral density. So the relation between them can be given into the z domain by this expression. So in this expression, on to the left hand side we have the power spectral density represented px of z. So this is in terms of the z transformation of rx of k, which is the autocorrelation function. So we have the summation where the index parameter k ranges from minus infinity to plus infinity over rx of k in multiplication to z to the power minus k here. Now if we can have the natural logarithm of the LHS here, so it becomes ln of px of z. So this can be expanded into a Laurent series. So the Laurent series expansion or the natural logarithm taken over the power spectrum representation into this expression can give this form here. So this representation is, we have ln of the power spectral density px of z. So summation k is equal to minus infinity to infinity ck into z to the power minus k as it is. So in this representation with the help of Lorentz series, this ck is nothing but the representation of coefficients of the expansion. So here ck is nothing but the representation of the coefficients of the expansion. So this expansion by the use of Lorentz series we have shown with the help of z domain representation. If we switch it to the Fourier domain representation, both are belonging to the frequency domain. So here we go, this is the expression where we have L of px as a function of e to the power j omega. So px of z and px of e to the power j omega, these are the same. So this is the power spectral density into the Fourier domain and this is into the z domain. So here we carry out the Fourier transformation. So summation k is equal to minus infinity to plus infinity over ck, the same coefficients, into e to the power minus j times k omega. So here these ck can also be taken into the form of Fourier coefficients here. So these Fourier coefficients can be computed in this particular expression here. So here we have c of k obtained by taking 1 upon 2 pi integral ranging from minus pi to plus pi over the natural logarithm taken over px of e to the power j omega into e to the power j times k omega d omega, the differential of the angular frequency here. Now in addition to this representation of ck, the component c of 0 can be also expressed here. So this c of 0 is basically proportional to the area under logarithm of the power spectrum. Here it is the mathematical expression to represent the same. C of 0, 1 upon 2 pi integral minus pi to plus pi ln of px as a function of e to the power j omega d omega here. Now the previous expression that we have represented into the Fourier domain or the natural logarithm taken over that particular power spectral density. So from the same expression, if we take the anti-logarithm, so from that we can get the new expression. This is for the px of z, again into the z domain also we can go for. So this is represented the exponential function of the summation k is equal to minus infinity to plus infinity ck into z to the power minus k here. So from this particular expression we can split it into the three forms. So as we have the range of k minus infinity to plus infinity, so by the next step we split this range into the three. So here we take the first component. The first component here it is represented as exponential of c of 0, and the another one exponential of k is equal to 1 to infinity the summation carried over ck into z to the power minus k, and the last one is the exponential of the summation of k is equal to minus infinity to minus 1 ck z to the power minus k. So you can focus your attention onto these particular ranges. The 0 has been explicitly taken out into the first component, the positive side is into the second component, and the negative side of these numbers for the k assignment is taken into the third component here. Now this particular representation that here we have, so from the second component, the middle one, we can have the representation. So this definition gives the representation of exponential of k is equal to 1 to infinity the summation carried over c of k into z of minus k, provided mod z is greater than rho here. So this is nothing but the representation capital Q of Z. At the very beginning, we have stated what exactly the spectral factorization can be. So this is what the middle factor we have represent thereupon. Now here Q of Z may also be expanded into the power series form. The power series form can be the representation by this mathematical equation where Q of Z is expressed into 1 added to small q of 1 into Z to the power minus 1 added to Q of t into Z to the power minus 2, which can go further here. Now, as into the previous equation where we have shown the three components for the power spectral density represented into the Z domain, the last component can be expressed in this particular form. So here onto the left hand side you can find it exponential of k to the range minus infinity to minus 1 over k into Z to the power minus k. This was the component here. Now changing or switching the order of summation here. Here we have made k is equal to 1 to infinity. So that time in place of this c of k Z to the power minus k, we must write here c conjugate k into Z to the power k only. So by the next step, we make it to the form exponential of the summation k is equal to 1 to infinity, we keep the same. This is ck into 1 upon Z conjugate to the power minus k. So this can also be represented from the previous represented of q of Z, nothing but the q conjugate of 1 upon Z conjugate. So this substitution at the middle component and this substitution at the last component can give us the spectral factorization made into the simplified form here. Now this leads to the spectral formalization. The expression here we write, and the first component here we have represented sigma suffix 0 square. Rest of the two just now we have been discussed. Now this sigma 0 square, generally the representation of variance is with the sigma square here. So this is nothing but the exponential of c of 0, which can be computed by having the substitution from one of our previous formulation. In place of c of 0 we have that previous formulation. This is 1 upon 2 pi integral minus pi to plus pi natural logarithm ln over px as a function of e to the power j omega d omega here. So this is what the spectral factorization, this particular expression must have been outlined here. Now if this sigma 0 square is a real and a non-negative, so this spectral factorization is the best one here. And for the real valued random process, the spectral factorization can take the expression of the form. Here we write px of z is equal to sigma 0 square q of z and q of minus 1. There won't be any need of the conjugate representation here. So after this we shall discuss the three properties with respect to the regular processes one by one. So let us start with the first property. So the first property is nothing but any regular process that can be realized as the output of the causal and stable filter that is driven by the white noise having a variance of sigma suffix 0 square here. So this is also called as the innovations representation here, and that can be also illustrated in the following diagram here. So in this particular diagram we have v of n feeding as input to this particular filter function h of z. So at this time we have the power spectral density denoted into the z domain pv of z is equal to sigma 0 square here, and after filtering will be over here we obtain x of n. So the corresponding power spectral density px of z is nothing but sigma 0 square into h of z into h conjugate of 1 upon z conjugate here. So this is what the representation here we have, and it is called as innovations representation of the process here. Now moving to the second property here. So in the second property, it is stated that the inverse filter, if we have, so whatever we have seen into the first property here, the same input feeding and the output receiving sequence is to be reversed here. So that time the required filter function is nothing but the inverse of the previous. So it is 1 upon h of z here. So it is called as a whitening filter here. So x of n is filtered with 1 upon h of z. Then the output is a white noise and the variance is sigma 0 square here. So this is also further illustrated, and here it is represented. So the representation is in this particular diagram here. So in this representation, here you find x of n is fed as input, and here we have 1 upon h of z, the filter function. We obtain v of n. The corresponding power spectral densities have been represented, and these representations have been reversed with respect to the previous into the property number 1 here. Now the last property is nothing but, if we have v of n and x of n as discussed before, so these are related by the invertible transformations here. So either the processes may be derived from the other here, so therefore they both contain the same kind of information here. So this is all with respect to the spectral factorization as discussed here. To conclude this particular topic, we are going to see one illustration. This illustration shows the symmetry constraints that are placed onto the zeros of a power spectrum of a real valued random process, and when the power spectrum is a rational function of z here. So in this particular illustration, you can see the symmetry constraints with respect to z1 and 1 upon z1, z2 and z2 conjugate like this, z3 and z3 conjugate. Here it is 1 upon z3 conjugate, 1 upon z3. So here we have the horizontal real part of the axis into the z domain. This is imaginary part of the axis into the z domain here. So the reciprocal zeros have been represented here, and this is what we find the unit radius circle, we call unit circle of zeros here, and the conjugate reciprocal zeros have also been represented in this particular illustration. So with this information, we conclude our topic spectral factorization.